Alright, in this chapter we're going to learn how to graph the trig functions. We're going to begin with the sine and cosine functions in the first section before we move on to the other trig functions. And we're going to start kind of simple with making a sketch of just y equals sine x and y equals negative sine x, and then y equals cosine x and y equals negative cosine x. On this next page, we've got a table set up for us to kind of find some values, and I included the unit circle here just because then we could grab those values that we need quickly without needing to use a calculator. So we're starting with sine, and remember that the sine of an angle is the y coordinate. Also, we are plotting this graph where x is in radians. So at 0 radians, sine of 0 is 0, right? So again, we're just looking at the y coordinates of these values that are on this first column here. So sine of 0 is 0. Sine of pi over 4 is root 2 over 2. Now we're going to be plotting this as a point, so if you take the calculator and take square root of 2 and divide it by 2, you'll get about 0.707. Pi over 2, sine of pi over 2 is 1. Sine of 3 pi over 2 is root 2 over 2. Sine of pi is 0. Sine of 5 pi over 4, now down in the third quadrant here, is negative root 2 over 2. Sine of 3 pi over 2 is negative 1. Sine of 7 pi over 4 in the fourth quadrant here is negative root 2 over 2. And sine of 2 pi is 0. I selected these values just because I think we can get a decent idea of what it looks like plotting just these points. You could also include, if you want, the additional points for pi over 6 and pi over 3 and 2 pi over 3 and so on, and to kind of help see the shape a bit more clearly in the points that we plot. But I think that these ones will do a pretty decent job. Before we move on to the negative sine x, I'm just going to go down and let's plot these points. So here we have coordinate axes here. We're going to plot it from 0 to 2 pi. And what I'm going to do is I'm going to mark out, so 0 is obviously at the origin, and I'm going to say here's 2 pi over here at the end. And I'm just going to kind of cut this up. So half of that would be pi, half of that is pi over 2, and half of that is pi over 4. And this part, pi over 4, 2 pi over 4, 3 pi over 4. There's pi. Halfway in between pi and 2 pi is 3 pi over 2, or pi and a half. Then that in between would be 5 pi over 4, 6 pi over 4, 7 pi over 4. Okay. Now I could tell just by looking at the unit circle, and we see it as evidenced in the values that we wrote down in the second column here, that sine never gets bigger than 1 and it never gets less than negative 1. So I'm going to scroll down here again. I know I'm going to need to mark off my y-axis, so it only needs to go as high as 1 and as low as negative 1. And the other point, so we know that we could see that the sine function takes on the values 0 and 1 in the ones that we marked down, but then we also have this root 2 over 2 and negative root 2 over 2. So I'm going to mark that value off as well. So root 2 over 2, which is approximately 0.707, which is maybe like right there, and negative root 2 over 2 around here. Okay, now I think we're ready to plot our points. So the sine x, so at 0, and I'm just plotting the points that we have in the table. So sine of 0 is 0, so I'm going to put that point there. Sine of pi over 4 we said was root 2 over 2. So that gives us the point pi over 4 root 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is root 2 over 2. Sine of pi is 0. Sine of 5 pi over 4 is negative root 2 over 2. Sine of 3 pi over 2 is negative 1. Sine of 7 pi over 4 is negative root 2 over 2. And sine of 2 pi is 0. So now we have these points, and the next thing we want to do is connect them. Now when you're plotting a graph, when you're sketching a graph by plotting points, we do not simply connect the dots with straight line segments. We want to draw a smooth curve that goes through all of these points. And that's going to look like this. So this is a graph of y equals sine x. Next, we're going to plot y equals negative sine x. We don't necessarily need to refer to the circle again because we're just going to take the values that we found for sine x and change the sign, right? That's what this means here. So this is still 0. This will be negative root 2 over 2, negative 1, negative root 2 over 2, 0, positive root 2 over 2, positive 1, positive root 2 over 2, and 0. So now if I take these points, again, I'm taking the x-coordinate, and then this is going to be the y-coordinate, right? So the first column, the x's, and then my y-coordinates I'm going to get from the third column here. That's going to look like this, and I'll do this in a different color. So at 0, we're at 0. At pi over 4, negative root 2 over 2. At pi over 2, we're down here at negative 1. At 3 pi over 4, negative root 2 over 2. And at pi, we're back to 0. At 5 pi over 4, we're at root 2 over 2. 3 pi over 2, we're at 1. 7 pi over 4, back to root 2 over 2. And at 2 pi, we're back down to 0. And if I draw a smooth curve, again, I'm not connecting the dots here. This isn't straight line segments, but if I draw a smooth curve that goes through these points, it looks like this. So this is y equals negative sine x. We could make some observations, or at least I guess one general observation is that the blue curve seems to be just the same shape as the black curve. The difference is that the blue curve is reflected across the x-axis, right? If the x-axis were a mirror and we held it up, it would flip everything over. And that's what we see happening in the blue curve. The other thing is, you'll notice we only plotted the points from 0 to 2 pi. There's no need to plot any more. I mean, it's not that the angles can't keep going. I can have angles bigger than 2 pi, but then those values just repeat itself, right? So I get all the values of sine as I let theta, or x, range from 0 to 2 pi, get all the angles in the circle. And once I get to angles bigger than 2 pi, I'm just repeating the same values. So we say that this function is periodic for that reason, and there's a repeating pattern, and we only need to graph one go around the circle, basically. If I did graph further out, it would just be the same pattern, the same kind of wave that would repeat itself forever. So now let's do the same thing with the cosine function. The cosine function, we get those values from the unit circle by taking the x-coordinates. So again, I took the same values of x, the same angles. So 0, pi over 4, pi over 2, 3 pi over 4, and so on, right? So I went up by increments of pi over 4. And those x-coordinates are here. So at 0, cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 2 is 0. Cosine of 3 pi over 4 is negative root 2 over 2. Cosine of pi is negative 1. Cosine of 5 pi over 4 is negative root 2 over 2. Cosine of 3 pi over 2 is 0. Cosine of 7 pi over 4 is root 2 over 2. And cosine of 2 pi is 1. Again, the cosine function, I don't have to go any further than from 0 to 2 pi because I get all the values if my angles kept going. I would just get the same values repeated again. So we can plot these. Again, root 2 over 2 is approximately 0.707. So I'm going to do the same thing. I'm going to mark out the end of the unit circle going out to 2 pi at the end, and then half of that would be pi, half of that would be pi over 2, and then in between pi and 2 pi is 3 pi over 2. Half of pi over 2 is pi over 4, so pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. And go up as far as 1, as far down as -1, and then root 2 over 2 is about there, and negative root 2 over 2 is about there. So at 0, cosine starts off at 1. So it starts off right there at root 2 over 2. At pi over 4, we're at root 2 over 2. At pi over 2, we're at 0. 3 pi over 4, we're at negative root 2 over 2. At pi, we're down at -1. 5 pi over 4, negative root 2 over 2. At 3 pi over 2, we're back to 0. At 7 pi over 4, back up at positive root 2 over 2, and at 2 pi, we're back up at 1. Now I want to draw a smooth curve that goes through these points. And that goes about like that, right? So it doesn't have to be perfect, but it should be a smooth curve that matches these points as best as I can make it. So it's a similar kind of behavior. It's this wave behavior. In fact, if I continued the curve, you could see we get that same kind of wave behavior. It looks more like the sine curve, just like kind of shifted over, basically. So now we can turn our attention to the negative cosine. And as we did on the last page, I'm just going to take the values that we already wrote down in the middle column here. I'm going to change the sign. So I got -1, negative root 2 over 2, 0, positive root 2 over 2, 1, positive root 2 over 2, 0, negative root 2 over 2, -1. Okay, now I'm going to plot these points. So it starts here at -1, then we're at negative root 2 over 2, at pi over 2 we're at 0, 3 pi over 4 we're up here at positive root 2 over 2, at pi we're at +1, at 5 pi over 4 we're at root 2 over 2, at 3 pi over 2 we're back to 0, at 7 pi over 4 we're at negative root 2 over 2, and at 2 pi, oops, we're not at 0, at 2 pi we're at -1. And so if I connect, a smooth curve, right? I want to draw a smooth curve that fits these points as best as I can. And it looks like that. So this is y equals negative cosine x, and the black curve here is y equals cosine x. Alright, so we see like the same relationship between the black and the blue curve as we saw on the last page. The blue curve basically is a reflection of this black curve. I'm just kind of flipping the graph over across the x-axis. I'm going to show you kind of an illustration. We use the unit circle to get these points, right? And basically, you could imagine taking, marking a point And then just imagine that the unit circle is a free spinning wheel, right? So it's on a spoke here, or a little axle in the middle, and it's like a bicycle wheel. And as I spin the wheel around, the cosine is simply tracking where the x coordinate is. Likewise, for the sine curve, I do the same thing, right? I mark a point on this wheel, and as I spin the wheel around, the sine curve just marks where is the y coordinate. And you could see this in action. I'll do the sine curve first. So you could see here's the unit circle on the left, and it's going to, on the right, plot out, keeping track of the y coordinate. X is the angle in radians, and so as I move out, you'll notice, so they put x in green, and they marked green as like the arc length. So remember that when you measure an angle in radians on the unit circle, that is just the length of the arc. So what we're doing is comparing the length of the arc with the y coordinate. And as we go through the circle, you could see it plot out that sine curve that we just graphed. And you could see the same thing with the cosine. So the cosine, we're keeping track of the x. So now there's three things to look at. We have the unit circle. Then they gave us this sort of intermediate graph below, where we're plotting the angles. They plot the angles here on the y-axis, and then they keep track of the x coordinate. And you could sort of see there's that dotted line there that just keeps track of what is your x coordinate. And then over on the right, they've just flipped the graph because we are graphing y equals cosine of x. So we're plotting those x coordinates onto the unit circle onto the y coordinate of this curve. Right, so again, just imagine this as a wheel spinning around, and the graph just keeps track of the x coordinate. All right, so now we're gonna make some changes. We know how to deal with, we know what happens if we just put a negative sign in front of sine x or cosine x, but what if we put another number in front of that? We're gonna graph y equals 2 sine x and y equals 1/2 sine x. And you might find it helpful to be able to refer back to the unit circle, but sine of 0 is 0. So 2 times sine of 0 is still 0. Sine of pi over 2 is 1. So 2 times sine of pi over 2 is 2. Sine of pi is 0. So 2 times that is still 0. Sine of 3 pi over 2 is -1. So if I multiply that by 2, I get -2. And sine of 2 pi is 0. So 2 times that is still 0. You'll notice I didn't include as many x values. I just did kind of where it's 0 and where it hits its peaks and valleys. But I know that the sine curve now is a basic wave. So I'm just plotting and keeping track of where those peaks and valleys are hit. And then I'm going to still plot that wave shape that we discovered in the last examples. So I'm plotting out to 2 pi. Half of that is pi. Half of that is pi over 2, and then this point here is 3 pi over 2. I'm going as far up as 2, and as far down as -2. So at 0, I'm just plotting the points that we put in the table there. Pi over 2, we're at 2. At pi, we're back to 0. At 3 pi over 2, we're at -2. At 2 pi, we're back to 0. Again, we are not drawing straight line segments. We're drawing a smooth curve. We know that the sine function has this smooth wave shape. So there's sine of 2 times sine of x. Now for the other graph here, it's 1/2 sine x. So I'm going to plot those points. Again, sine of 0 is 0, half of that is still 0. Sine of pi over 2 is 1, half of that is 1/2. At pi, we'll be back to 0. Sine of 3 pi over 2 is -1, half of that is -1/2. And sine of 2 pi is 0, so half of that is still 0. So I'm going to plot those points. We start at 0. At pi over 2, we're at 1/2. At pi, we're back to 0. At 3 pi over 2, we're at -1/2. At 2 pi, we're back to 0. Drawing a smooth curve that connects these looks something like this. So the effect that this number sitting out in front of the function, right, 1/2 sine x or 2 times sine x, seems to affect how where its peaks and valleys are, where its maximum values are and minimum values are. The basic behavior is still the same. It's still this wave shape, but it just affects kind of how high up it goes, how far it strays from this sort of equilibrium of 0, right, of the x-axis. And this number in front we call the amplitude. In fact, the amplitude is actually always positive. The amplitude is the absolute value of a, right? So if we're looking at a times sine x and a times cosine x, the amplitude is the absolute value of a. It's just an absolute measure of how far it strays from that equilibrium of 0. And if a is negative, it has that, it still has a positive amplitude, but if it's a negative value, it just means it'll also be reflected across the x-axis. So let's sketch a graph of -3 cosine x. So we'll just note that the amplitude is 3. Right? And then it will also be reflected. So what I'm going to do is sketch a cosine curve with an amplitude of 3. So I'm going to mark out my x-axis going out to 2 pi. Half of that is pi, right? I think we're all kind of getting used to these values here. 3 pi over 2. I need to go as high up as 3 and as far down as -3. And it's also going to be reflected. Now, I'm going to go back to where we plotted the cosine and the negative cosine. Cosine x begins at its peak, and negative cosine x begins at its negative peak, right, at its minimum. So this is a negative cosine function, -3 times cosine, so it's going to begin at the minimum of -3, and then at pi over 2 it's back to 0. At pi it's going to reach its max. At 3 pi over 2 it's at 0, and at 2 pi it's back down to its minimum. And then I'm going to draw the cosine curve through that. So when we're graphing these sine and cosine functions, we know the basic shape of sine and cosine, and then we're just trying to fit it to this additional information about what is its amplitude and is it reflected or not. So this is basically, so far we know the effect of having a number in front and whether or not that number is positive or negative, how that will affect the graph of sine x and cosine x. Now we're going to take a look at what happens when we multiply, not in front necessarily, but what happens if I multiply inside, if I multiply that argument by a number. So the period of the function, I mentioned that these functions, they just kind of repeat the same pattern, this wave pattern, and because it repeats itself, we say that the function is periodic, and the period is the length of how long it takes before the function just repeats itself. So far, when we've been working with sine x and cosine x, the period is 2 pi, right? Because we went once around the circle. And we know that if we keep going, it'll just repeat those values. And putting a number in front, so a times sine x or a times cosine x, that doesn't change the period, right? The number in front just changes how far it strays, changes what its maximum and minimum values are, but it doesn't change the fact that it still is just one go around the circle. Changing the period happens when we multiply inside the function. So the period of sine x and cosine x is 2 pi. The period of sine of bx and cosine of bx is 2 pi over b. And the reason for that is that if I think about y equals sine x versus y equals sine of 2x, for example. So sine x, I'm kind of spinning the circle around, or letting the x go around the circle. This basically just says go around twice as fast. I have this multiplier inside. Go around twice as fast. And if I go around faster, it doesn't take me as long to get all the way around the circle, right? Here, x only has to go from 0 to pi in order for the argument 2x to go from 0 to 2 pi. And so for that reason, the period of y equals sine 2x is 2 pi over 2, or just pi, and that's sort of what we just kind of illustrated or observed right here. When we're sketching a graph, I just want to kind of put down, like, in words, the idea of what we're doing here. We're going to first find the period and the amplitude, right? So the amplitude, we're just going to look at that number in front. The amplitude is always positive. We find the period using 2 pi over b, and then we split up the period into fourths, right? Just like I did here, right, when we were graphing this. I said, okay, the period of this function is 2 pi, and I just went out to 2 pi, and then I cut that period up into fourths to get pi over 2 and pi and 3 pi over 2. And then we're going to mark down where the function starts, where it meets its peaks and valleys, its maximum and minimum values. So we're going to do an example here. We're going to do a few examples, actually. And we're going to start with sketching a graph of y equals sine 2x and y equals sine x. So for y equals sine x, the amplitude is 1, because that's 1 times sine x, and the period is 2 pi. For y equals sine 2x, the amplitude is still 1, and the period is 2 pi over 2, or pi. So I wanted to write down the information for both graphs first, because the longer period, I need to account for the longer period when I mark off my x-axis. So I need to be able to go out as far as 2 pi. So there's 2 pi, half of that is pi, and this is pi over 2, and this is 3 pi over 2. So I can actually, and they both have the same amplitude, so I only have to go as far up as 1 and as far down as -1. So I'm going to go ahead and sketch sine x right off now. So sine starts at 0, it hits its peak at pi over 2, back to 0, then its minimum here at 3 pi over 2, and back to 0 at 2 pi. So it looks like this. Now, for sine of 2x, its period is pi, and I need that period cut up into fourths. So I've already got pi and pi over 2 marked down, so I'm going to go half of that is pi over 4, and then half in between there is 3 pi over 4. So plotting these values, I get 0, pi over 4 will be at 1, at pi over 2 will be back to 0, at 3 pi over 4 will be a -1, and at pi will be to 0 again. So that's, whoops, that looks kind of like that. Now, I could keep going, right? I mean, I've got the period marked out. You know, my x-axis keeps going. So if I wanted to, I could sketch another period of this function. There's 5 pi over 4, 7 pi over 4. And I know that the pattern just repeats itself. So 5 pi over 4 will be back at its peak. At 3 pi over 2 will be at 0. 7 pi over 4 will be at -1. And at 2 pi back to 0. So here's y equals sine of 2x. And in black is y equals sine x. So multiplying by a number bigger than 1 inside the function, right, as we've done right here, means that I'm kind of going around the circle faster, and I can kind of fit more periods in the same length. It kind of squishes it together horizontally. If you could sort of imagine, you know, it's almost like an accordion, like kind of squeezing it together, we get more waves in the same period. Let's do another one. Now we're going to sketch a graph of y equals cosine x over 2 and y equals cosine x. So again, I'm going to begin by just marking out the information about each of these functions. Y equals cosine x, the amplitude is 1, and the period is 2 pi. For y equals cosine x over 2, first I want to see it as cosine of bx. You know, the coefficient on x, x divided by 2, is the same as x times 1/2. So that's cosine of 1/2 x. So this amplitude is still 1. The period is 2 pi divided by 1/2, which is 2 pi times 2, or 4 pi. So there's the period for cosine of 1/2 x. So that has the longer period. And so basically, and that should kind of make sense, you know, when we say cosine of 1/2 x, we're saying we're going to go around the circle half as fast. We're going around slower, so it should take longer for it to make a full revolution around the circle. So as I mark out my my x-axis, I need to be able to accommodate the biggest period, so that's 4 pi. Half of that is 2 pi. Half of that is pi, and then over here we're at 3 pi. I will, let's see, marking out the amplitude. We're at 1 and -1. I'm going to go ahead and sketch cosine of x over 2 first, since I've got that information marked down. So cosine begins at its peak. It's at 1. And then at pi we'll be at 0. At 2 pi we're at -1. At 3 pi back to 0. At 4 pi at its peak. And so this looks something like this. So this is cosine of x over 2. Next, we'll graph the cosine x. Cosine x has a period of 2 pi, so I've already got pi and 2 pi marked out. So this is 3 pi over 2. This is pi over 2. And I'm going to sketch that one in blue. So again, cosine starts at its peak. Then it's going to hit 0 at pi over 2. At pi, we're down at the minimum. At 3 pi over 2 back to 0, and at 2 pi back to the maximum. And so here's a graph of y equals cosine x, together with the graph of cosine of x over 2. So we can see the effect, really, what that this coefficient in front of x has on the graph of cosine. Okay, let's do another. We're going to sketch the graph of y equals -2 times sine of 3 pi x. All right, so things are getting a little bit more complicated. Let's write out our information. The amplitude is 2, and then I'll just say it's also reflected because there's the negative. And the period is 2 pi over b. Now in this case, b is equal to 3 pi. So 2 pi over 3 pi is 2/3. So this has a period of 2/3. So notice now for the first time we're not going to be having any pi's on our x-axis. My amplitude is going to go as far up as 2, as far down as -2. Now let's finish marking out the period. So we're going out to 2/3. Half of that will be 1/3. Half of 1/3 is 1/6. And then here's how I do this. I've got 1 over 6, 2 over 6, 3 over 6. 3 over 6 is 1/2. And so those are my markings on the x-axis. And now what I'm going to do is just fit the behavior of the sine function in here. I know that sine starts at 0, and it's reflected. So sine x starts at 0 and it goes up to its peak. But if it's reflected, it's going to start at 0 and then move down. So at 1/6, it's at its minimum. At 1/3, it's back to 0. At 1/2, it's at its peak. At its maximum. At 2/3, back to 0. And there's the graph of -2 times sine of 3 pi x. All right, the last thing that we're going to look at when it comes to graphing sine and cosine is a phase shift. A phase shift is a horizontal shift. When we are working specifically with periodic functions, we call it a phase shift and not a horizontal shift. Any function could be shifted horizontally. When it's a periodic function, we say it's a phase shift. We know there's a phase shift if we're adding a constant term inside the sine function. So it's that plus c at the end. So maybe I might be multiplying x by, something other than 1, like maybe I could be adjusting its period or not. But when I see that plus some constant or minus a constant, I know there's a phase shift. Now, to see what the phase shift is, how much we're shifting by, it is not just going to be whatever that constant is a lot of the time. What we have to do first is factor out that coefficient on x inside the parentheses. And when we do that, we get something like this. And it's this guy right here. There's our phase shift after we factor out the coefficient of x. The phase shift is to the left if we're adding it. It's to the right if we're subtracting it. So we're going to do some examples here. We're going to graph the function 1/2 sine of x plus pi over 4. So I'm going to first just mark down some information. The amplitude here is 1/2, and there is no reflection. The period, now the coefficient on x is 1, right? Like b is equal to 1. That's a 1x. So the period is 2 pi. We're not changing the period. And because the coefficient on x is 1, the phase shift is simply the pi over 4 that we see. And when I write down the phase shift, this is important. I'm going to write down how much and also the direction. That's a plus pi over 4, so it's going to the left. And I'm going to keep that in mind as I mark out my my x-axis. I'm going to make sure I have room to move to the left by pi over 4. So here's 2 pi, there's pi, pi over 2, 3 pi over 2. My amplitude is 1/2. And so what I'm going to do first is I'm going to first sketch a graph of the 1/2 sine x. So I'm going to first sketch it without the phase shift. And 1/2 sine x, it starts at 0, then it reaches its peak, then it's back to 0, then it's at its minimum, then it's back to 0. So here's one half sine x. Now these points that I plotted, I'm just going to take each of these points and move them to the left pi over 4. I think of these points that I plot as like the anchors of the graph, because once I set down the anchors, then I can fit the curve to those points. Now I'm just going to move each of these anchors pi over 4 units to the left. So the amount pi over 4 is half of pi over 2. So I'm marking this first so I could sort of see that, well, pi over 4 is about this long, right? It's about that much. So then that's about negative pi over 4 here. Then in between that's 3 pi over 4. And in between that is 5 pi over 4. And in between those two is 7 pi over 4. And I'm going to just move each of these points over. And now I'm going to sketch this curve. And this is the graph we want. This is 1/2 sine of x plus pi over 4. Okay, let's try another one. In example 5.9, we're going to sketch a graph of y equals -3 cosine of 1/2 x minus pi over 8. So we're going to mark down this information. The amplitude is 3, and there's a reflection because it's negative. Before I go any further, I'm going to begin by rewriting the function. So our function is -3 cosine of 1/2 x minus pi over 8. And I'm going to stop myself, I'm going to make myself slow down, because I can tell that the phase shift is not just pi over 8, because there's this coefficient on x we have to take care of. I'm going to factor out the 1/2. When I factor out the 1/2, this is x minus pi over 4. And after factoring out the 1/2, now I could see that this is my phase shift. Is pi over 4 units. And it's a minus pi over 4, so it's going to go to the right. When I indicate the phase shift, I want to make sure that I include the direction. The period is still 2 pi over b, and b is equal to 1/2, and I could tell that by looking at, you know, in the as given or as after I factored it out. So 2 pi divided by 1/2 is the same as 2 pi times 2, or 4 pi. And I think we're ready to start. So I'm first going to sketch the function without the phase shift. So the first thing I'm going to do is sketch -3 cosine of 1/2 x. That has a period of 4 pi. I have to make sure that I have space to move out over to the right a little bit to accommodate the phase shift. But pi over 4, as it compares to the full length 4 pi, is pretty small, so I think I could put the end of the period out there. So this is 2 pi, there's pi, there's 3 pi. The amplitude is 3. Now cosine starts at its peak, at its maximum. Negative cosine is going to start at the minimum. So I'm going to do this one lightly in gray. I'm going to plot my points here. At 0, we're going to be at -3, the minimum. At pi, we'll be at 0. At 3 pi, we're at the maximum. At 2 pi, we're at the maximum. At 3 pi, we're back to 0. And at 4 pi, we're back to the minimum. So here is -3 cosine of 1/2 x. Now these anchor points, I'm going to just move each of these 5 anchor points, to the right by pi over 4 units. But first I have to kind of figure out how big pi over 4 units is. So my first step is from 0 to pi here. So half of that is pi over 2, half of that is pi over 4. So that's just a small shift. So I got to be able to move to the right by pi over 4, and I'm going to find the rest of these just by adding pi over 4. So this guy right here, after 2 pi, I'm going to take 2 pi over 1 plus pi over 4. I can get a common denominator. So that's 8 pi over 4 plus pi over 4. That's 9 pi over 4. So let me write that one above. Okay. And so I did that one. Oh, you know what? I forgot to do the one after pi. So there's that's halfway in between, so there's a quarter of the way in between. So pi plus pi over 4, that's 4 pi over 4 plus pi over 4 is 5 pi over 4. And then after 3 pi, getting a common denominator, that's 12 pi over 4 plus pi over 4 is 13 pi over 4. And then one more, so that's about that amount. 4 pi over 4, 4 pi over 1 plus pi over 4. So getting a common denominator, 16 pi over 4 plus pi over 4 is 17 pi over 4. Okay, now I will plot my points. So I'm just moving each of these points over by that amount. So there's that point, there's that point, there's that point, and there's that point. Okay, now there's the graph we wanted. -3 cosine 1/2 x minus pi over 8.